So I did my schooling in India, but then I came here to US 15 plus years back, and for my postdoctoral research. And then I got into my first job at Seagate Technology, which is the R&D job, followed by my job at Boston Scientific here as the engineering manager. So before coming to US, I have spent a couple of years in Europe and in Australia as well as a researcher and postdoc. So, as Mr. David asked, when we want to think about the opportunities for the uh, basic science people and the engineering people, um, especially in the industry side, there are abundant of opportunities available in the sense that we need to uh, get a deep understanding of the science, and if we are able to uh, perform well in the areas what we are going to specialize, there are plenty of opportunities in industries. So that's what I mentioned earlier in the first day, that doing a science course or even engineering doesn't mean that we need to get into software engineering or get into a school job or a professor job in a university. So there are a lot of opportunities in industries. So a couple of ways you can come to Europe or in US for higher education. So as I did for the postdoctoral fellowship here, and then you can get into a job, and then you can start your own research and things like that. So there are a lot of opportunities here, and yeah, we can talk about that if you want to reach out to me. I'll be happy to help you out. So with that said, let's move into our topic today. So I changed the title a little bit as nanotechnology and its industrial applications, but of course I'll be talking about the high frequency and the med devices and things like that. So before going there, I just want to give you some background about the company Boston Scientific, where I work. So our motto or our vision is to serve the patients in this rapidly changing healthcare environment. So we actually concentrate on our mission and values, which is that our company is dedicated to transforming lives through innovative medical solutions that improve the health of patients around the world. So Boston Scientific is a medical devices company, and if I want to give you an analogy, so you guys might have heard about Apple and Samsung, which are the two key players in the handheld devices market. The same way, Boston Scientific and Medtronic are the two big companies which play in the med devices sector. So medical devices means it's everything. So I'll talk about that a little bit later. So our strategic, our guide for growth is through strengthening our category leadership, and then kind of expanding into high growth market, and also driving global expansion. So with that, for doing all this, we need to have a good funding, and of course, our business and the company is a $59 billion worth company with 35,000 people around the world, with office locations in 15 countries. So we have the backbone to expand our growth as well. So with that said, so let me skip this slide, and let's get quickly into the products that we actually produce That is like we do R&D and then we manufacture these products and send to the market. So we have medical devices for neuromodulation. So these are nothing but the electronic implantable devices that could be put inside your brain that help patients to manage chronic pain and neurological conditions. So you would have heard about the opioid crisis here in US as well as in other countries. So to tackle those problems, we have this the devices we call the neuromodulation devices, which actually creates some electrical signals that will try to act against the pain signals that's traveling to the brain and thereby minimize the effects of the pain to the body. So that's the neuromodulation device. And we also make cardiac rhythm management devices like pulse pacemakers, defibrillators, afibrillators, etc. So there are also electrophysiology treatment and the mapping devices. So how what is happening inside the body, what is happening inside the heart. So we have devices that we could wirelessly watch how things are behaving inside your body. Also, the interventional cardiology, where we are having devices through which we can do minimally invasive treatments for the patients with vascular conditions. Then we manufacture devices in the endoscopy area, also for urology and pelvic health. So these are kind of the body parts where we make devices to make things work for the patients. Okay, so let me skip this one as well. And so these are the names of few devices that we are making. So we have made 19,000 devices from the day when the company was started, and currently we are making 260 plus devices for various conditions. So the Watchman is one of the popular devices of Boston Scientific because this is the only company that's making this device. And to give you a quick background on that, so this is meant for arterial fibrillation. So arterial fibrillation means your heart will have a irregular rhythm. That is the top part of the heart, which means that the blood is not pumped out properly outside the heart. So what happens is the blood will stay back inside, and it will be a clot, and then the clot will start to move to your brain. If it is moving to your brain, you will get a stroke. If it is going to your eyes, you are not going to see anymore. So that's the condition called arterial fibrillation. And this is the one and only device here in US which actually able to save you from that condition. So currently, before this, the doctors used to give the blood thinners like warfarin, coumadin, etc. But the blood thinners doesn't play the role like these devices because they depend on so many other things like the food you eat. Based on that, you need to adjust the medications and things like that. So this device actually gets into the area where the clot will happen, and it will make sure that the clot is not happening. And So this was very successful, and this has been very popular, and the doctors recommend this. So once the patients have this device, they are not taking any blood thinners anymore, and they just take an aspirin and they live with that. So let me stop there with this Watchman device, and you can get into our website to see all the devices. Okay, just give me a second. So with that said, now we can jump into the plan for today's discussion. So I will talk about the high frequency applications, and then I will touch on the hard drive applications and give some background on the medical device applications. So as I mentioned earlier, I have carried out research in the high frequency military applications in collaboration with Professors Bob Camley and Zbigniew Selinsky in Colorado, and also with Professor Bijay Kwanar at the JNU, who was talking about this high frequency applications yesterday. Also, as I mentioned earlier, I was a former employee of Seagate, so I have worked in a hard drive, especially on the reader and writer research. And currently, I'm working at BSE, so I have some background on the med devices. So with that, I could talk about all these three topics to some extent, of course. So please sit back and relax yourself as I walk you through the topics, okay? And if you have any question, let me know. I'll try to answer. Okay, so what are these high frequency devices? So as we talk about these high frequency devices, if you have attended yesterday's session, Professor Bijay's session, he introduced several devices like filters, isolators, circulators. So all these are the devices that come to our mind, which are used in the RF and the high frequency communications. So for today's session, we will focus on filters. And out of that, I'm going to pick a band stop filter as an example. So if you see here, the idle filters will have very sharp edges, sharp rising edge and a sharp falling edge. So for the low pass filter, it actually passes low frequency and stops at particular frequency and stops all the frequencies greater than that particular stop frequency. The high pass filter actually passes all the frequencies more than the given frequency. Bandpass filter passes all the signals within a given frequency range, and band stop is opposite to that. It will stop all the signals within a given range. So we all know these are the basic filter technologies used in various high frequency applications. So Dr. Bijay was talking about the military applications and then the drone application, etc. yesterday. So these filters are used in all these applications. But if we get into a realistic filter, so you will see that there is no sharp drop at the edges, rise or fall. It's all going to be going smoothly down, or it's going to smoothly rise up. Also, you would see sometimes this region where it is going to fall and become zero, there might be a gap, which means that there is a loss, which we call as eddy current losses or other losses. So we are not going to get into that now. So with that said, the usual filters are the passive and the active analog filters, and that's what the LCR circuit and all these things which we studied in our high school and the college physics, and they all operate at a very low frequencies. So by low frequencies, I mean kilohertz and megahertz frequencies. So if we think about very high frequency, so that is in the gigahertz range, we cannot use these filters, which on the left hand side showing something around from 10 to 40 megahertz frequency. So we cannot use these filters if we want to think about very high frequencies. And as I mentioned earlier, the uh, the military applications and the drone applications, all these happens at this very high frequency. So we need to have some device which would work at this high frequency. So that's what I mean by high frequency devices. And throughout this discussion, I'll be focusing on the band stop filter at this high frequency region. So, okay. So now I'm moving to the next application, which is the hard drive application. So I don't know how many of you have opened up the hard drive to see what is there inside. There are n number of parts, but there are a couple of important, or we can call as the primary parts of a hard drive. So the first one is the GMR element or the reader that reads the signals. And the other one is inside this head gimbal assembly, which is the writer, which writes the information that we want to be written in the drive. And then comes the electronics, which is the brain or logic. So you would see there are a lot of errors that could occur in a drive, and all the logics inside this electronic board takes care of those issues. And this is the media which actually stores all the information that you are going to write. So these are the major parts of the hard drive, and we will be talking about these parts as well, and how nanotechnology is playing a role on these parts. So with that said, so let me start with this GMR element or the reader. So what is this GMR element? So if you see the drive, as I mentioned earlier, you can the left-hand side photograph shows the disk, and there is the head, which is flying on top of the disk. So the picture below that shows the head clearly. So this is, if you can see the scale here, it is at a millimeter scale. And within that millimeter scale, you could see how small it is. So here you can think of as Boeing 747 flying on top of the ground with a few millimeters of space. So it is just flying with the 600 at 600 miles per hour on top of ground at 1 or 2 millimeters gap. So you can think of that and use the same analogy to think about how the head is flying over the disk in a drive. So that's the tight space we are working on here. So it's like a few nanometers above the disk. The head is flying. So the second picture here with the integrated lead suspension slash pico slider, that is the other angle for this picture on the left hand side in the second row. And the one which is magnified there is the head. That is, that comprises both the read and the write head. And if you see inside that, the red area, so that is our read head, which we call as a GMR sensor. So you can see that there are several layers within that small area, and all these are few nanometers thick. Like so, the nickel ion, the permalloy free layer is like 7 to 10 nanometers thick, and also all these thicknesses depends on the product and the densities we are looking into, and what kind of right field what is the nature of the media we are going to use. So all these play a bigger role in choosing the material for the different layers, and also choosing the thickness for these different layers. And so you have spacer, and you have a pinned layer, which is again another strong or hard magnet. And also you have some magnetic antiferromagnetic film for exchange bias and things like that. So we are not going to go into that now. So this is the reader structure. So this is the element which, when you start to click your computer, as soon as the computer starts, this is what's happening. Your reader, this element on the right hand side, which sits on this thing which flies on the media, goes and starts to read, and that's why we have the computer opening up with your login, asking your login and things like that. So then let me focus on this area, which you can see there is a tip here, and this is what is the write head. So when you type a Word document and you want to save that, so what is happening in the drive is this write head is going to convert your ones and zeros convert your data into ones and zeros and store that in this media. So this whole thing is nothing but an electromagnet. So by electromagnet, I believe everyone might have studied in the high school physics and the college physics. So you can produce magnetic field by applying electric field. So you have the electromagnet that produces a magnetic field based on the information it receives, whether the information is 1 or a 0. So all your data, whatever you're typing in the Word document, like how are you, is converted into ones and zeros through the electronic board, which I call as a logic. And that ones and zeros are converted into magnetic field, and that magnetic field writes or transforms the magnetic field in the media. So we will talk in detail about that later as well. So that's how the information is written, and I will come back to this writing and reading in the later part of the presentation. So this is the second element, which is the write head. And then the third element is the media. So this is the media, and the first triangle kind of shape is the blow up of that media, and we can see at the end the third picture on the left hand side for the media, which is called as a conventional media. There are very small grains here inside on the media. So these grains are very few nanometers of size, like So the grain size would be a couple of nanometers, and of course, 5 nanometers or 6 nanometers. So depending on what kind of write head you're going to use, these sizes differ. And also there is a limit for the size of this grains, because there would be a lot of other issues, like one grain flipping the other because of the interactions and things like that. So let's not get into that for now. And on the on the other side, there's a different type of media, which is called the pattern media. So if you see here, this orientation in the media is what that defines the ones and zeros. So you can see that the the region between the up and the down, that transition is called 1, and down to up is called the 0. So like that. So just imagine that the blues are 1, and the ones without any color is 0, or the other way around. It's all convention what we are going to use here. So as we gone through the hard drive applications, so there are like 4 major parts. Of course, we are not going to touch on the electronics, but we are looking into the writer, the reader, and the media. So all have nano structures embedded inside that. So that is going to play a bigger role in defining the capacity of the drive, is it like a 5 terabyte drive or a 10 terabyte drive? So now you can see that you can get 20 terabyte drives. So of course, there will be a big session coming up tomorrow, and I believe on Friday, where my Seagate colleagues will be talking in detail about the modern drives and the modern technology, but we are not going to get into that now. So this is about the hard drive applications. And now we will get into the third application, which is the medical device application. So the the important aspect of medical device is the ones I talked earlier is all like kind of an implantable devices, the devices that goes into the human body, and they do certain things. But these are kind of device, not exactly a device, but kind of a device that goes into the bloodstream and work for us. So one is the nanoparticles for targeted drug delivery. So if you see here in this picture, so the small particles here are the nanoparticles, and the red or orange, whatever color you're seeing on the screen there, they are the kind of the disease particles. Let me stop there. I don't want to get into the details. We'll talk about that later. And so these particles, the nanoparticles, are actually coated with some ligands. So usually the drug-loaded carrier composed of the magnetic core, which is at the center, and the biocompatible coating material, because it's actually interacting with the body, so it needs to have this compatibility, the biocompatibility. So the magnetic core is usually made of iron oxide or iron, and there are n number of nanoparticles for this. And the coatings are made of materials like gold, SiO2, etc. And also, based on the biokinetics of the particles, a drug carrier ranging from 100 to 200 nanometer in diameter is optimal for the in vivo delivery. Okay, so um, depending on where these particles are going to go, we can choose the size of the particle, because a kidney can tolerate any particle which is less than 10 nanometer, while our liver and spleen can tolerate something like 200, more than 200 nanometers. So by toleration, I mean that clearance of these particles. So once the particles do their necessary function inside the blood or inside the body, they need to be excreted outside the body. So all the particles which are less than 10 nanometers are excreted through the kidney, and which is called the renal clearance, and the large ones are sequestered by reticulo endothelial system of the spleen and the liver. So depending on what we are going to do, or depending on what we are going to target, we can choose the size of the particles, and also the therapeutic agent here, which is the ligand, and that's the one which helps the particle to move towards the right target. So this is the first medical device application we are going to talk, which is the targeted drug delivery. Okay, so the next one is similar to this, but it's kind of a medical device application called the magnetic hypothermia or tumor treatment. So there are several therapies here. One is the one I mentioned now, the hypothermia, the magnetic hypothermia. So the other ones are the photothermal therapy and the photodynamic therapies. Of course, I just listed out here for your information, but we are not going to talk about that. Of course, they have these are the nanoparticles used for the photothermal therapies and the photodynamic therapies. So this is very important because for usually the most common way of treating cancer or the tumor is chemotherapy. So I think you guys might have heard about that. This is what I would say is it's like a carpet bombing of human body. So like you have terrorists in a country or in a area, and you just go and drop a bomb there, as it was happening in World War IIs and all, where destruction happens everywhere around that area. So that's called the carpet bombing. And here, the chemotherapy is like kind of a carpet bombing of the human body, because it affects both the cancer cells and also the normal cells. So you will feel the people who are having chemotherapy, they have a lot of side effects. So you can see the hair loss and things like that. Those are like a kind of things which we could tolerate, but there are other things which are happening inside the body which the patients would not be able to tolerate. So for this kind of situation, we can use the programmable nanoparticles. So by means of programmable, I'm trying to say that they have a complementary ligands outside the surface of the nanoparticles that goes and attached to the tumor cells. So when we have a programmable nanoparticles, it could reach the cancer cells directly without damaging other tissues. So since the nanoparticles are very small, like a few nanometers, they can go around other things in the blood, and then can reach to the site very easily. And it would be like a so I can call this as a programmed missile hitting the target precisely. So nowadays we have all the Sorry, any question there? Okay.
Participants, kindly mute your microphone, please. Kindly don't distract.
Thank you. So this is like the missile. Now we program with all the infrared and ultrasonic information. So it goes and hits the target precisely. So that's what I call these nanoparticles. These are going to hit the tumor cells precisely, and I will show you how it's going to do that. So that's one important application of nanoparticles in the medical devices. The second one is the tumor ablation. So that's what I'm showing here in the next slide. So what happens here is, so these nanoparticles, when they are exposed to some external magnetic field, they will create heat, and this heat will be able to kind of kill the problematic cells or the tumor cells, and thereby we don't need to have the external chemotherapy or external therapies to kill those cells. So the right hand picture here shows the experiment that usually people used to do in mouse, and how these cancer cells, which are red in color, are being killed by the magnetic nanoparticles, which are black. And once they do their job, which is the cell apoptosis, they will they are excreted outside the body through the normal ways, which I explained to you earlier. So this is called the magnetic hyperthermia, where you heat the region and kill the cells. So this is a very important treatment for the cancer cells. So another research that's happening in diabetes. So we have come across diabetes. That's a more common issue or disease that almost all Asians are having because of the because of the food habits we have, like the sugar and the carb we are eating. So let's not get into that now, but there is a good research happening in diabetes where nanoparticles are used or targeted to the cells, where it would deliver insulin for that cell growth and regenerate tissue at the target location. So again, these nanoparticles can be programmed, and then when they go to the target cells, they can deliver some substances that would help the cells to grow. So here, in the case of diabetes, it's the insulin that's getting delivered to those targeted cells, and they also send other substances which would help the cells to grow. So that's a good research happening, and it's promising. They have done a lot of work on the mouse, and slowly it would get into human soon. So another application here is in neurology. So one big issue working in brain or neurology is you need to cross the blood-brain barrier. So by blood-brain barrier, I mean it's a physiological barrier. So for example, sometimes if you take some medication, like Perinam, they used to call like to avoid vomiting or so. When you take some medications like that, you will feel some dizziness or something like that in your brain or in your head. So that's because that particular tablet or medication is able to cross the blood-brain barrier. So that's what I call as a blood-brain barrier. And these nanoparticles are so small they could reach the remote areas in the brain, crossing this blood-brain barrier. So, how it could be helpful? We can now target the right areas in the brain to treat the neurological disorders because they can easily travel and cross that blood-brain barrier. So there are several applications using nanoparticles for treatment of conditions like diabetes, cancer, and neurological disorders. So that's the second med device application I want to point out. The third one, this is kind of a brand new, which is working in a lab and in animals. So these are the nanorobots. So nanorobots are current trend in med devices. So scientists are actually developing these nanorobots that goes in our bloodstream that could be used to uh, diagnose and also treat as well as monitor the health conditions. So these robots are able to swim through our blood and move into the slippery glues like our eyes, our eyeballs. So they are able to easily traverse inside the body. So these nano-sized diagnostic devices, so they will be able to detect the chemical changes in our body. So, for example, chemical changes in our body on the spot in real time. So, I think you might have heard about, or everybody have come across the situation like going to a laboratory and taking the blood, and they do the biochemistry of your blood to say, yeah, so this is all normal. So you have components in your blood a little bit higher, so you might have this problem. So those kind of things you will see, but that will happen only after the reaction has happened and that has come to your blood. So, for example, chronic conditions like, yeah, let's take heart failure or the diabetes. They often lead to complications um, uh, kidney failure. The high blood pressure will also lead to kidney failure and the heart failure and heart attacks. So these could be prevented by constant monitoring of these various biomarkers. So biomarkers in the sense, I mean the elevated levels of the components in the blood. So at present, what actually happens? Mostly, we are caught in a shock when these abnormal biomarkers are found in our random blood work. So we go to a doctor for something else. He asks us to do some blood work, and we find that, wow, our creatinine levels are high, or something is high in our blood. So that means things are happening, and it's often too late to prevent complications sometimes when we haven't found that earlier. So imagine how this will be helpful if we have something in our body, like a body of patients who have high blood pressure and who have extreme diabetes. So you have something in your body that is constantly monitoring and inform us immediately when there's a chemical change happening in the blood. So these devices, which I call the nanorobots, they could be programmed to get levels of any biochemicals in the blood, and it would able to communicate to your phone. So this is kind of the real-time tracking of patient's health status, and that's what is happening in the nanorobotics. So nanorobots are also used to target, as we were talking with the nanoparticles. So they are used to target the cancer cells or the disease tumor cells and kill those cells. And nanorobots are also used for assisted surgery. And as I mentioned, they are also used for biosensing. So these are kind of the third application of nanoparticles or nanotechnology in mid devices. So we have gone through three different applications. One is high frequency, some technology application for missiles or for drones or in for high frequency. Next, we came into the hard drives. We talked about the applications there. And at the last, we talked about the med devices, different targeted drug delivery and things like that. So, what physical phenomena is common in all these applications? Can you guys think a little bit on this? Can you see something that's common across all these applications? Yep. So, the common thing here is magnetism. So, in the first one, the high frequency application, we haven't talked what the material we are using, but you can reach that high frequency only if you are going to use magnetic materials. But when we came to the hard drives, we also talked about the media, which is like a magnet, the reader and writer. All these are all magnets. And also, when we came to nanoparticles, we talked about nanoparticles, but we didn't say whether it's a magnet or so. But now I am going to explain you how these are magnets there. So magnetism is the physical phenomena that connects all these three applications. So magnetism is nothing different to us because we have studied magnetism in our high school. We have played with magnets. So you guys would remember like putting a magnet under a paper and having some iron powder or so and moving that. So one magnet will interact with the other magnet. So all these are well-known phenomena, and we have all studied that. And that is the basic for all the top level technologies that we are talking now. So let's get a little bit dive into this to see what exactly plays a role in magnetism in those technologies what we discussed earlier. So we know that while a magnetic field can be induced by a current, and a current can also be induced by a magnetic field. So we can use the curl right hand rule to talk about the magnetic field produced by the current carrying conductor. So you all remember that you can use the right hand grip, point your right thumb in the direction of the current's flow, and curl your fingers around that. And this curl or the direction of the fingers will show the direction of the magnetic field. So that's all common. We have seen that. So there is no new science here. The same thing goes for ferromagnetic levels at an atomic level too. So what do I mean by that is we have studied about the electron orbitals. So we know the Hund's rule, how the different orbitals are filled up. So within this, we know that for magnetic perspective, the most important and the interesting of all these are the 3D orbital. So that's this 3D 10. And by 10, it means that it can occupy 10 electrons in it. And again, when we can go into the periodic table and talk about the elements there. So I'm just getting into the very basic chemistry here to talk about this. Um, so before we move further, I have a request to Mr. Paul. Can you please remind me when we have last 15 minutes or so?
Sure, sir. Okay, sir.
Thank you. So this periodic elements, we have gone through that several times in our life as we were moving from our school to college. So these D block elements are the important elements as far as magnetism is concerned. So we can see that um, the Pauli's principle will always hold when the electron starts to fill up the different orbitals. So we can go through that. So when we talk about scandium, it has one electron in the d orbital. So likewise, we can keep going. Titanium, one electron, vanadium, one electron, chromium, and manganese, one electron there. But when we get to iron, it starts to get paired, but then there are a lot of free electrons. So keep in mind one thing. When you read magnetism, sometimes people confuse themselves telling that free electrons will help magnetism. Like free electrons are the ones responsible for magnetism, but that's not the case. So there are complicated quantum mechanics involved here, like the exchange interactions, etc. Um, so materials made of atoms with the filled electron shells have a total dipole moment of zero because the electrons all exist in pairs with the opposite spins. So we know that the electrons can spin and also orbit around the nucleus. So this is the basic one which we have studied. And since it's an electron and it's spinning and it's moving around, we can call this as a current flowing through something. So for a moving current, there will be a magnetic field. The same way, these electrons will have a magnetic field. So the unpaired dipoles we simply call as spins, even though they also generally include orbital angular momentum, and they tend to align in parallel to an external magnetic field. So these are all concepts of quantum mechanics, why we need to consider spin and why they are going to align with the external field. So we are not going to get into the spin statistics theorem and the quantum mechanics here. But just to mention that, I want to show you that starting from iron, cobalt, and nickel, these are the permanent magnet. I can call it as mostly useful magnets, whether it is metal by itself, or if it's an alloy with something else, or if it is made as a nanoparticles. So all the three elements are used in those three big applications which I talked to you earlier. So let me quickly go through this one, and let's come to this point, which is the ferromagnet. Of course, we talked about that. So these are permanent dipoles, even though they also generally include orbital angular momentum. They tend to align spontaneously without any applied field. Okay, so this is like all the spins pointing along the same direction. But when they are true ferromagnet, all the moments align within the domains. But in total, the magnetic field is zero because the domains will be aligned in different directions. And usually, due to the internal field generated, they will tend to cancel each other. So that's another concept we need to talk, which is called the demagnetizing field at the edges of any magnet. So these materials have a permeability, so they are nonlinear in nature. So we will see that a little bit later, and they have a value greater than 1. And above Curie temperature, these materials are paramagnetic. So that's the relation between the uh, paramagnets and the ferromagnet. So here, iron, cobalt, and nickel are the ferromagnets, and these elements. So here, the d orbital elements are also called the transition elements, and here these elements here are the gadolinium and etc. So they are ferromagnet below the room temperature. So let me skip all these ones. And the other type of material are antiferromagnets. Here,
Can I interrupt, please?
yeah, please.
Sir, now we have 15 minutes to go for your session. Sir.
Okay, okay. So the antiferromagnets have alternating layers of spins, and they align in opposite direction, which means that the sample has no net magnetic moment. Okay, so the same way we can keep explaining about the antiferromagnets, and there are also different magnets called ferrimagnets, and I'm not going to get into the basics here on the diamagnets as well. So let me skip all these ones because we have a little more slides to go through. So yeah, let me go through these basic magnetism principles. So you guys might have come across this hysteresis loop in your school and college. And this hysteresis loop, keep in your mind for now. I will come back to this when I'm going to explain the hyperthermia, because this area is what is going to generate the heat in the nanoparticles hyperthermia ones. So the next one important concept in magnetism that's being used in the other applications there is ferromagnetic resonance. So what happens here is, I told that the ferromagnets have a spin, and when you have an external field, these spins will try to rotate about the external field, and we call this as a precession. So you can see that all these are the free spins, and this is all spinning about the RF field that we are going to apply to this ferromagnet. So you have the external field applied to keep all the magnetic moments aligned, and you give an external RF field like an oscillating field, and these spins will start to precess around the applied magnetic field. So this is called a ferromagnetic resonance. So keep that in your mind. So what happens is, during ferromagnetic resonance, so these electrons absorb the energy because it needs some energy to spin around the applied field. So it absorbs energy from the radiation that's going to fall on these magnets. So by radiation, I mean the RF frequency. Okay, so this is one of the second concept, which is very important, and it's used in applications. So the third one is magnetoresistance, which is called the GMR effect, the giant magnetoresistance, for which they awarded the Nobel Prize in 2007. So what happens here is the any electron can have up and down spins, and so they have a low resistance when two layers are aligned in the same direction, like on the top, and when they have an anti-parallel alignment, the resistance is very high, which means that electrons cannot pass through the material. So you have two layers of material, and the magnetic moments, if they are parallel, then they can pass through. If they are anti-parallel, they are scattered and they are not able to pass through. So that's called the very simple concept of GMR, or giant magnetoresistance. So this is the concept that's being used in hard drives. So I will come to that quickly. And so I'm putting a figure here to show. You can see that the magnetic moment here. So if you go to the previous one, by X, I mean that it is opposite. So you can see the resistance is high, and as this magnet moment turns towards this reference layer, the resistance drops. And you can see that here, when they are aligned, when they are on the same directions, the resistance becomes zero. That's all. This is called the magnetoresistance. It's a very simple concept, and for this, they were awarded the Nobel Prize. Okay, so this is another way to show the GMR. I want to quickly show this. So you can have the up and down electrons, and you have two layers here, iron, chromium, and iron. And when they have same orientation, the electrons can pass. And if they are the opposite orientation, you can see that the electrons cannot pass. So that's what the 1 and 0 when we go into the magnetic recording. So I think it's the same one. Okay, I'll skip these ones. I don't want to get into this because we don't have time to cover these ones. So these are similar to what Professor Bijay was showing yesterday. So now we have magnetic structures, and I told you that when you apply an RF field, the magnetic moments will absorb that energy and they will try to process. So this y-axis is transmission. So you send a signal and the energy is absorbed inside the material. So when it comes out, it will loses its energy. And this happens at one particular frequency where the spins are going to process around the applied field. And you can see that the energy has completely dropped, which is called the ferromagnetic resonance. And this is exactly the technology which we are using for our filters. So the band stop filter, which I showed earlier in the first few minutes. So you can see that any signal around this frequency, 14 gigahertz here, or in the 17 gigahertz or the 19 gigahertz, would not be passing through if I am going to make a filter using this ferromagnet. So that's the resonance condition, which is playing a role in the filter. So the next one, of course, I want to skip. So next one is the magnetic recording. So what exactly happens here in the magnetic recording? So you have the slider, which is on top of that, and this is the disk, which is rotating down. So I want to show what magnetic concept, the GMR effect, how it's playing a role here in the magnetic recording. So you have the disk here, and you have the so here I showed the magnet here, and it has a coil around that. So this is a simple electromagnet, and I'm going to pass my data ones and zeros. So when it is 1, think that the applied field is high, and when it is 0, think that the applied field is low. So when you have a high applied field, and when you have a media which is all like a magnet, so this applied field is going to turn the media or the magnetic field in the media, and that will be recorded as ones and zeros. So this is the media, and you can see that you can have ones and so this is the region where it's not turning the magnetic field in the media, so it is 0, and when it turns, it will become 1. So that's how the this layer in the media is made of thin magnetic layer, and that thin layer, which is a nano layer, acts as a small magnet, and this magnetic field from the writer turns those magnets up and down, and that's how the information is stored as 1 and 0. So that's where the nanomagnets come into play. So that's how 1 and 0s are recorded. And on the return, so now I'm going to read the information. So when I read, the magnetic field in the media would be ones and zeros depending on the direction it's going to face. So if it is up, let's think that the magnetic field is more, which means that the reader, you saw that they have a giant magnetoresistance. So it will push the free layer in the reader along the direction of the top layer. So I will be passing current through the coil, and this current will be getting out because the spins can pass through this layer. So when this happens, it will record as 1. But when the field is 0, so when it is 0, so for example, in this region, there is no field, which means that the layer is not going to turn along the direction of the top layer, which means that according to GMR principle, they are opposite oriented, which means that the current cannot pass through. So that means there is no record. So it's called a 0. So that's how 1 and zeros are read from the media. So again, we have very nanometer thickness layers for these readers, and that's how the magnetic nano layers play a very important role in magnetic recording. So with that, let me quickly go into the magnetic hyperthermia. So I told you that to remember those hysteresis loops, which we looked into when we were talking about the ferromagnets. So here I have these magnetic nanoparticles. Okay, so these are the magnetic nanoparticles which have spins, as we talked earlier. And now I'm going to apply an RF field to this magnetic nanoparticles. So RF field means it's going to change in direction. That means the field is going to flip back and forth. That means what happens? These magnets will be going back and forth. These small nanoparticles will be moving back and forth like this. So slowly, as I increase the frequency of my RF field or the alternating magnetic field, so you can see that these nanoparticles start to move fast. So as they start to move fast, they will generate heat. So this is the heat which actually able to kill the tumor cells around that. So I think there is another one in the next slide which will help you to see how it's going to kill those. So sorry, it's the same one. Yeah, it's here. So you can see that these nanoparticles are coming inside, and let's have these yellow regions as the tumor cells. So this, you can see that this is very small, so it is not affecting any of the other good cells like the red ones. So it is going to the yellow cells now, and these nanoparticles, the magnetic nanoparticles, are going to be there. And now what happens is we are going to apply some magnetic field, external magnetic field. So these particles are starting to move back and forth due to this alternating field. So it's going to generate heat, and you can see that it's killing these tumor cells slowly, and that's how this targeted tumor hyperthermia works. So the next one is the nanorobots. So how the concepts that we studied now, or as we gone through now, are helpful in nanorobots. So you can see that these nanorobots have a lot of small pin-like structures, and what exactly it is doing here is, so let me stop here. So usually when we want to do some biopsy. So currently, what we are doing is we insert this device inside the body, and it has this kind of a knife thing at the end. It grabs a big amount of tissue, and we take it for biopsy. But instead, so if we are going to use the nanoparticle like this, so it's going to go here. So that's what it's doing. It's going here, and then it's picking the tissue, a little bit of tissue, because it's a nanoparticles, so it's going to pick only very small amount of tissue, and it's going to come out. And so these particles, tentacles, can be adjusted, or it actually can be made of materials that would change its orientation based on the chemical composition of the blood, or chemical composition of the tissue where it's going to reach. So there are a lot of engineering work that could be done here, and this example is in a pig that's been done. So this is a very great application. And when these nanorobots are made of magnetic nanoparticles, we are able to track these robots clearly using our MRI. So, that's another big concept, magnetic resonance imaging. So, at some point of time in your life, everybody will get into this MRI to get our body scanned for some other reason. So, MRIs will be able to play a role here to track these particles where it goes, and we can also apply external fields to move these particles as well. So there are a lot of research happening on this area, which is again based on the basic magnetism principle. So this is on the nanorobots. So let me click to the last slide, which is the another kind of nanorobots, which is being developed at University of Cambridge. So we talked about this. This could travel around, travel inside the blood to go and diagnose or kill the tumor cells. And that's exactly what this simulation is going to show. So you can see that this is going inside the blood, and it sees the tumor cell there, and it actually sends some chemicals, or depending on how we are going to, also depending on what kind of tumor cell it is, you can send the RF wave. Again, if you are going to have a magnetic nanoparticle inside this, it will generate heat and kill those tumor cells as well. So one very important application of this kind of nanorobot is it is able to have cameras, and it can diagnose what's happening inside that, which I was talking earlier when we were discussing about nanorobots for diabetes and other kinds of applications. So it's going to be very helpful there. And the second one is this, again, when embedded with magnetic nanoparticles, we can track the movement of these particles inside the blood. So that's a great application of nanoparticle here in nanorobots for diagnosis. So I think that's the last slide I have, and I believe I have finished this on time. Thank you so much for listening. Any questions, let me know. And you have my email as well. If you have anything, any questions, or any other than or questions related to this talk, or other than this talk, you can reach me. Thank you.
Thank you very much, sir, for your very insightful lecture covering the high frequency applications, hardware applications, and medical device applications. We profusely thank you for your very valuable time and for considering to partner with us for this program. And we look forward to your continued support and patronage. Dear participants, due to paucity of time, we will adjourn this session. Should you require any clarification from the resource person, Dr. Veera Kumar, we request you to kindly leave the questions on the chat box, so that he is from the US, and it's an odd time for him also, so we don't have to disturb him. We will send the questions on his mailbox so that at his convenience he will revert to us, and we will circulate the responses to all the participants on your respective emails. So I think that will be the ideal way. So let's not draw any more time from the resource person, because we know the time difference is also very odd. Once again, we would like to profusely thank you, sir, for your very valuable time and for your expert lecture. Thank you very much, sir. Thanks a lot.
Yeah, great. Thank you so much. And one thing I want to mention to the young students there is, as I told earlier, focus on the basic sciences, master the skills there, and that would open up abundant opportunities for you guys. So good luck for everything. Thank you.
Thank you very much, sir. Thanks a lot. Thank you. Shiba ma'am, good morning.
Good morning, sir.
Ma'am, shall we start our session, ma'am?
Yes, sir, we can start our session.
Yes, ma'am. Welcome to the resource person of the second technical session of the second day. We have with us Dr. K.N. Shiba from the NIT Tiruchirappalli. As you know, dear friends, NIT Trichy is again one of our institutional partners for offering this 5-day short-term certificate course on nanotechnology and its applications. And before we get into the session, let me introduce to you the resource person of this session. And we welcome you, ma'am, for this online platform and for this course. And we once again thank you for your time. And there have been a lot of rescheduling your session, and ultimately we could get you. We were very particular that we want to have you for this program, and therefore we have got you for this program. Dear friends, Dr. K.N. Shiba is currently an assistant professor in the Department of Chemical Engineering at the National Institute of Technology, Trichy, Tamil Nadu. She completed her BTech in Chemical Engineering from Madras University and MTech in Energy Engineering from Bharatidasan University, Trichy. She later pursued her doctoral degree in Energy Engineering from the National Institute of Technology, Trichy. She has undergone several short-term courses from various institutions of higher learning, including a month-long training in biomass gasification at University of Saskatchewan, Canada, based on which she has set up a laboratory on fossil and alternate fuel processing laboratory at NIT Trichy. Previously, she worked as research associate at the Regional Engineering College, Trichy, and as lecturer at Shastra University, Tanjore, Tamil Nadu. She is a member of the Board of Governance and a doctoral committee member, besides serving as a reviewer of various internationally accredited journals. She secured the Young Scientist Award from the Department of Science and Technology and the Most Inspiring Women Engineer Award conferred by the Engineering Watch, New Delhi. She has guided over 50 PG projects and has undertaken various major R&D projects such as combined pyrolysis and steam gasification to establish multi-fuel production with maximized hydrogen yield undertaken through the Department of Science and Technology, Government of India, and another project titled Monitoring of Seabed and Seawater Quality through the Ministry of Environment and Forests. She has published over 25 research articles in internationally reputed refereed journals, published her contributions in over 30 conferences, workshops, symposia, and proceedings. She has also authored books published by Lambert Academic Publishing Company, Germany, and Stadium Press, USA. She has participated in several conferences, seminars, and symposia on different aspects and has organized many workshops, conferences, colloquiums, and seminars. She has also delivered several invited talks widely across the country. On academic foreign visits, she has delivered series of lectures in various higher learning institutions across Canada, Malaysia, and Dubai. Her other professional interests include biomass, bioenergy, and industrial safety. She is a member of various learned societies such as Solar Energy Society of India, National Society of Fluid Mechanics and Fluid Power, Institution of Engineers, Indian Institute of Chemical Engineers, the Society for Advancement of Electrochemical Science and Technology. So with this brief introduction, we would like to hand over the platform to Professor K.N. Shiba, who will deliver the lecture titled Nanomaterials as Photocatalysts. Over to you, madam. Thank you so much.
Thank you so much, sir, for the nice introduction. Good morning, all participants. Sir, can I know the nature of participants, background of participants?
Ma'am, we have a multidisciplinary gathering of students across the country from NITs, IITs, and various technological institutions. Besides, we also have science graduates, computer science graduates. So it's a mix of students, madam, both engineering, technology, and science.
Okay, sir. Okay.
Thank you.
So, 1 minute. Okay, so I just asked this question to know, because I'm basically a chemical engineer, turned into an energy engineering. Right now, I'm focusing on energy-related chemical engineering for applications, sir. So I just thought, okay, to get to know the background of participants, I can elaborate them.
Okay, ma'am.
Okay. So good morning, all. So shall I share my presentation?
Yes, ma'am, please.